For the longest time, getting a robot to do exactly what you wanted meant spoon-feeding it massive, and I mean massive, amounts of specific, active interaction data. But what if a machine could learn how the physical world actually works just by watching it? Right here in the V-JEPA abstract, we see the core thesis: developing models that can genuinely understand, predict, and plan in the physical world. But here's the real secret sauce. They do this by combining internet-scale passive video observation with just a tiny, literally almost microscopic amount of actual robot interaction data. It's a complete game changer for embodied AI. AI's World Model Challenge and the Blueprint of Cognition. This quote from Jan LeCun pretty much hits the nail on the head. He says a major challenge for modern AI is to learn to understand the world and learn to act largely by observation. This builds on cognitive theories going all the way back to Craik in 1967. As humans, we build an internal model of the world just by taking in sensory inputs, right? We watch, we intuitively grasp the laws of physics, and then we act. Now, previous related work in AI went a different route, heavily relying on state action sequences and explicit reward feedback, classic reinforcement learning. Or, on the flip side, some recent approaches tried generating exact full-pixel videos to plan. But that wastes an insane amount of compute just trying to predict shifting shadows or a blade of grass moving. So this research asks, can an AI learn a focused predictive world model in an abstract representation space mostly just by sitting back and watching? Which brings us to part 2, scaling video pre-training, or learning by watching. To build their foundational Video Mix 22M pre-training dataset, the researchers gathered over 1 million hours of action-free internet video. Just think about that scale for a second. They pulled from a bunch of diverse sources. We've got something V2 for first-person egocentric video, Kinetics and How to 100M for third-person exocentric views, and then a massive curated chunk straight from YouTube. That's 1 million hours of purely passive observation. No robot commands, no rewards, just visual data of the world doing its thing. The model learns simply by masking out parts of these videos and trying to predict the missing representations. So to actually process this colossal dataset and bake general self-supervised visual understanding into the encoder, their pre-training recipe required 4 key scaling ingredients. First up, data scaling, jumping from 2 million to 22 million videos. Second, model scaling. They bumped the architecture up to over 1 billion parameters using a massive vision transformer. Third, longer training. They used a warm-up, constant decay learning rate schedule. Basically, this lets the model stabilize early on before efficiently chewing through all that data. And fourth, higher resolution. By progressively scaling both the spatial and temporal resolution during the decay phase, the model learned to handle longer, sharper video clips without totally blowing up the compute budget. Okay, moving to part 3, the action-conditioned world model, known as V-JEPA-2AC. This right here is where things get mind-blowing. We just went from over 1 million hours of passive observation to build a foundational understanding of physics, but to post-train the model for action conditioning, they used a remarkably tiny dataset of just under 62 hours of unlabeled robot video from the Droid dataset. 62 hours. I mean, in the world of machine learning, that is a drop in the ocean. But because that foundational pre-training was so robust, 62 hours was literally all they needed. And that post-training gives us V-JEPA-2SE. It's a 300 million parameter autoregressive transformer network that essentially sits right on top of the frozen video encoder. It takes all that passive video knowledge and uses it to predict the outcomes of physical robot commands step by step into the future. Simply put, if a robot takes action X from state Y, V-JEPA-2SE can literally imagine what the resulting video frame is going to look like inside its learned representation space. Now for part 4, video understanding and prediction, where we validate this hypothesis. Before we even touch a physical robot, these benchmark results prove just how capable this model is. For probe-based classification on something V2, which tests fine-grained motion understanding, it hits a 77.3 top 1 accuracy. That means it accurately classifies complex actions just based on its internal representations. Then, for probe-based action anticipation on Epic Kitchens 100, it achieves state-of-the-art prediction with a 39.7 recall at 5. Translation, the correct future action is in its top 5 guesses almost 40% of the time, which is a massive 44% relative improvement over previous bests. And for video question answering, when they hooked it up to a large language model, it scored an 84.0 on perception test, totally dominating the 8 billion parameter class. The takeaway here, it's not just memorizing pixels, it's demonstrating actual temporal reasoning. On to part 5, zero-shot robotic planning. Taking it from thought to motion. This is where we reach the absolute bleeding edge. When we visualize what the world model is imagining based on identical arm movements, you can see its grasp of intuitive physics. The model correctly predicts that if the gripper is closed, the cup is going to move with the arm. But if the gripper is open, the cup just stays on the table. It naturally learned object constancy, shape constancy, and even gravity, purely from watching videos. And because it can predict the future so accurately, it can actually plan. Here, a Franca Emica Panda robot arm successfully executes a zero-shot pick-and-place task. How? Well, by minimizing a goal-conditioned energy function inside a model predictive control loop. Basically, you show it a target image of what you want, and the model rapidly samples possible actions, predicting which sequence of movements will make reality match that target image. It executes the first action, observes the result, and replans on the fly. And remarkably, it does all this zero-shot. It's successfully manipulating novel objects in completely new lab environments without any task-specific training or explicit reward systems. Finally, part 6, connecting observation to action. Let's synthesize all of this. The ultimate takeaway here is the sheer power of decoupling. By separating the action-free pre-training from the action-conditioned post-training, V-JEPA 2 proves that AI can learn how the world works exactly the way we do, just by watching it. Learning a joint embedding predictive architecture over millions of hours of web video creates a rock-solid bedrock of physical common sense. And once that foundation is there, you really only need a tiny sliver of actual robot data to teach the system how to use its body in that world.